This lecture is about the naive Bayes classifier, and I'm going to start with a brief revision of some notions of probabilities that we're going to need, and then talk about the Bayes classifier, which in theory would be an ideal classifier for solving classification problems, but we'll see that in practice it can hardly ever be used. So that would give us the motivation and the reasoning for the naive Bayes classifier, and this is one classifier that you will implement in the first assignment. So I'm going to talk about two applications of the naive Bayes classifier, both for continuous data like you have in the assignment, where you have features with numerical continuous values, and also an application to a classification problem where the features are categorical. And then I'm going to talk a bit about the details of how to compare different classifiers to see if the results are significantly different, and also some details on rescaling the data. To finish this lecture, I'll give a brief outline of the first assignment, and that will be covered mostly in the tutorial classes for this week and the next, which will be to help you in the first assignment. So let's start with some background on probabilities. You probably already know this, but it's good to remember so that it's easier to understand this Bayes and naive Bayes classifier. So this table that we have here gives us the joint probability distribution of two random variables. Variable x, which can take these values, 1, 2, 3, 4, and variable y, which can take these values here, 2 through 6. So each number here tells us the probability of x having one value and y having another at the same time. So the joint probability distribution, this part here, gives us the probabilities of all the combinations of x and y. Now, if we want to know what is the probability, for example, of x being equal to 1, and we have the joint probability distribution, we need only to add the probabilities of x being 1 when y is 2, when y is 3, 4, and so on. So if we take all the possible combinations of y for x equal to some particular value, and we add all those joint probabilities, we get the probability of x being 1 regardless of the value of y. So this is the sum rule, because we are adding the joint probabilities of x having some particular value for all combinations with the other random variables. So we are adding all these probabilities, and this probability of x having some specific value is often called the marginal probability, because we find it here on the margins of our table. So this tells us the probability of x being 1 regardless of what value y has, and the probability of y being 2 for any value of x. So this is one concept here, the marginal probabilities, and how we can get there from the joint probability distribution. Another important concept here is the relation between the joint probability distribution, the marginal probability, and the conditional probability. So the conditional probability of y having some particular value, given that x has another, for example, the conditional probability of y being 2, if we already know that x is 1, we'll not need to take into account all of these combinations, because we already know that x is 1, so x cannot be 2, 3, or 4. And if we want to know the probability of y being 2, if we already know that x is 1, then what counts is this 0.06 among all the possibilities for y if we fix x as 1. So this is the idea here, that the conditional probability of y being some particular value when we already know the value of x is the joint probability of x and y having these particular values divided by the probability of x having that value, because we are only counting this combination inside all of these values, which add up to the marginal probability of x. So we can write this way: the conditional probability of y having some value when we already know x is the joint probability of the two of this combination divided by the marginal probability of x, which we can rearrange, and we can say that the joint probability here is equal to the product of these two terms. So this would be the product rule. The joint probability of x and y, that is a particular combination of x and y, is the probability of y if x has that particular value multiplied by the probability of x having that particular value. Okay, so why do we want these concepts, the sum rule and the product rule? Because now we have these Bayes rules which can relate conditional probabilities of one variable as a function of the other. So the joint probability distribution, for the joint probability distribution, it is irrelevant what the order of the variables are, because the probability of having y equal 3 and x equal 1, it's obviously the same as having x equal 1 and y equals 3, because this is exactly the same place there in the joint probability distribution. But since we can rewrite this with the product rule, then we can reach this Bayes rule, which relates the conditional probability of y knowing x related to the conditional probability of x knowing y, and then with this operation. So we multiply by the marginal probability of y and divide by the marginal probability of x. So this is just a brief revision. This is probabilities. You already covered this in different courses. I'm going to give just a little side comment here. It's not relevant for this part of the subject matter, but we're going to come back to this a bit later. There are basically two important interpretations of probabilities. The classical one, the frequentist interpretation, sees probability as the frequency of some random event when we give infinite trials. So if we run the same experiment infinite number of times, the frequency that some random event happens is the probability of that event happening. So in this case, Bayes' rule simply relates frequency estimates from two different perspectives. So y knowing x and x knowing y, and we can just compute the relation between the two. The Bayesian interpretation is different. It sees probability not as the frequency of something that is random by nature, but as a measure, a rational measure of our uncertainty about something. So it's not about things being random, but it's about what we know of them. And in this case, we can see Bayes' rules as something that the probability of some hypothesis being true given some evidence would be related to the prior probability of that hypothesis multiplied by the probability of the evidence if the hypothesis is true, and divided by the probability of the evidence a priori, so regardless of whether or not the hypothesis is true. So this gives us a more epistemic interpretation of what probabilities are. So we're going to skip this for now. I'm going to talk a bit more about Bayesian learning further on in the course, but this is just to set the scenario here that we can interpret these Bayesian probabilities and the Bayesian rule in a different way. But for now, we are simply going to ignore these different aspects, and we're going to consider that for classification, we can use something like this. So the probability of some example belonging to some class given the features that we know. So this is the idea of classification. We can observe some things about the examples, but then we need to classify the examples in different classes. So the probability of the examples belonging to those classes, to any particular class, is the prior probability of belonging to a class. So we can see this, for example, if 80% of the data belongs to class 1 and 20% belongs to class 0, a priori we already have a larger probability of any given example belonging to class 1. So this would be the marginal probability of belonging to class 1. This is the probability of having those particular features if it belongs to that class. So how frequent these features are in that particular class, and then divided by the probability of any point having those features. So we can think of these either as frequencies or as a measure of the confidence with which we can assign the class. But either way, we can, if we estimate these probabilities from the data, we can classify our examples. So let's look at the Bayes classifier. We're going to use this rule, this relation, to try to find the class that is most probable. So in the Bayesian sense, the one that we find the largest probability for our data. So this is the relation between the two. The probability of belonging to a class, if it has some features, can be given by this expression. But note that the prior probability of any point having those particular features does not depend on the class. This is just the marginal probability of the features. So even though this value, the value of this probability here, is the result of this fraction, we can ignore this part because this will be constant for any class for that particular set of features, and we can say that the probability of a point with these particular features belonging to this particular class is proportional to the product of the marginal probability of belonging to the class and the conditional probability of having those features if it belongs to that class. So this is what matters, because now we're going to simply try to find the class for which this probability is higher, and we can just ignore the marginal probability of the point having those features. Okay, so since this product here is the same as the joint probability distribution of the features and the classes, so the conditional probability of having those features, if it belongs to that class, multiplied by the marginal probability of belonging to that class, is the same as the joint probability of having those features and belonging to that class. So basically we have two different approaches to classification here. We can either try to estimate this directly, the conditional probability of belonging to the class if we know the features, or we can compute the joint probability, and then with this, if we know the marginal probability of belonging to the class, and this is basically the proportion of examples in each class, we can then compute whatever we need from here. So all we need here is the joint probability distribution of the classes and the features. So this would be the Bayes classifier. Let's suppose that we know what are the probabilities of all combinations of features and classes. So we have the full table for the joint probability distribution of features and classes. If we classify each point, knowing the features, into the class that has the largest joint probability with those particular features, then we minimize the error, because we're always picking the one that has the class that is most probable for those points. So in this sense, the Bayes classifier is the ideal classifier. There is, if you know the joint probability distribution of features and classes, there is no other way of choosing the class to classify that gives you better results. You have to classify in the class that is most probable to occur with those features. The problem here is that this only works if we know the joint probability distribution. And this is a big problem in practice, because the joint probability distribution is the probability of all the combination of all the features and all the classes. So we need all these values in order to use the Bayes classifier. And in practice, this never happens, basically. So let's see an example here. Suppose that we want to create a classifier, or use the Bayes classifier, to predict whether or not some person will have diabetes. And we create a training set to measure these joint probability distributions with 20 questions. Let's suppose the questions are simply yes, no, to minimize the number of combinations. But we have 20 questions about the food people eat, the exercise they do, the blood pressure, age, things like that. So if we have 20 questions with yes or no answers, we have 2 raised to the 20 combinations, so about 1 million different combinations of answers. If we need to estimate the joint probability distribution of all these combinations and the 2 classes, we're going to need many millions of examples in order to have a large enough sample of all the combinations to compute the probability distributions. So you see, even with a simple example like this, the Bayes classifier is not feasible. We cannot, in general, without any simplifying assumptions, estimate the joint probability distribution of all the combinations of features with all the classes. So we have two things here. First, this is the basic idea. This would be the ideal classifier. If we could estimate the joint probability distribution, then we just assign the class that has the largest probability for those features, and we minimize the error in classification. However, in practice, we cannot get the joint probability distribution. We would need huge amounts of data in order to be able to estimate that adequately. So this is why we use the naive Bayes classifier. So let's add an assumption here. Let's suppose that if we fix the class, then the different features are independent. Now, this is a different concept from independence between the variables. This is just conditional independence. For example, suppose that we are measuring the time at which two people who live in the same block arrive at home. If we measure that time, we will see that there is some correlation between the two. So these are not independent variables because they can be affected by something like having a strike in the transportation system or an accident or something like that. But now suppose that we know what happened there. So we know that, for example, all the public transportation system was paralyzed. In that case, if we already know that, then whatever happens to change, to affect the time they get home, is now no longer interdependent. So this is the idea of conditional independence. The variables may be dependent, they may be related to each other, but given some specified event, for example, the class the point belongs to, they become independent. Now, in practice, this is very hard to actually happen, because there is usually some other relations that can keep the variables interdependent. But we're going to assume that for the naive Bayes classifier. In particular, we're going to assume that given the class an example belongs to, if it belongs to that specific class, then all the features are now independent of each other. So if we want to estimate the joint probability distribution of the class of the point belonging to this particular class K, and having this particular value for feature 1 and this particular value for feature 2 and so on, all the way to feature n, because the point can have n features, applying the product rule, this would give us the product of the marginal probability of belonging to this class, then the probability of having feature this value in feature 1 if it belongs to the class, then the value on feature 2 if it belongs to the class and has that value in feature 1, and so on. So this would be the expansion of this joint probability, and this is why trying to estimate this without any further assumptions is really impossible, because we need to take into account all these combinations. However, if we assume conditional independence given the class, then the probability of the point having some value at feature n, given that it belongs to this class and has all the other values at all the other features, just becomes the probability of having that value in feature n if it belongs to that class, because we are assuming that everything else becomes independent once we know the class the points belong to. And this makes the expression a lot simpler. So for naive Bayes, we can estimate, under this assumption of conditional independence given the class, we can estimate the joint probability distribution simply by the product of the prior probability of belonging to the class and the product of the probability of having each individual feature with that particular value if it belongs to the class, so conditioned on belonging to that class. And this is something that is much easier to compute. So in practice, we don't do this with products because these probabilities tend to be very small, and then we get underflow on the computations. But we can compute the logarithm of this and just add the logarithm. So add the logarithm of the prior probability and the probabilities of the feature given that class. And now the naive Bayes classifier will assign any example to one class that maximizes this expression. The logarithm of the prior probability of belonging to that class plus the sum of the logarithms of the probabilities of having those particular values on the features if it belongs to that particular class. So we do this for class 0, for class 1, class 2. This can have multiple classes, and we pick the one with the largest value. To train the naive Bayes classifier, what we need to do is to compute all these probabilities. So if we have the prior probability of belonging to the class, and this is simply the prior probability is simply the fraction of examples that belongs to that class. And if we compute the probability of having each particular value for each particular feature for each class, so in each class we're going to compute the fraction of examples that have each value in the features, then we know everything for classification. So when we need to classify, we just iterate through the different classes and compute this for each particular class for that point. The one that gives us the largest value is the class we assign the point to. So let's consider this example again, predicting if the person has diabetes. So we have these questionnaires with 20 yes/no questions. We start by splitting them into the group of people in the training set that are healthy and the group that are diabetic. These are the two classes that we are considering. And now inside each class, we count the fraction of yes and no answers for each class. So if we have, for example, 50 people in the healthy class, it's easy to compute the fraction of yes or no questions, yes or no answers for each question. We don't need much data for that. We can do the same for the people that have diabetes. And now we have all these values. So these probabilities are the probability of answering yes to question number 1 if the person has diabetes, or the probability of answering yes for the other class if the person does not have diabetes. And we do this for question 2, question 3, question 4, and with those answers we can then compute this expression. So now for the prediction, we just use the logarithms of the fractions, we add the logarithms of the fractions, we use also the prior, which is the proportion of diabetic or healthy people in our sample, and this allows us to find the class that has the largest value for these probabilities. Okay, so let's see a more detailed example. Suppose that we have this data set here. This has two continuous features. So these are not categorical, are not yes or no. They are these values here in the vertical and the horizontal axis that I'm representing. And we have two classes, the red points and the blue points. And we want to train a naive Bayes classifier for classifying this. Now, one way of doing this, we need to know the probability distributions of each feature for each class. So we want to know how for example, the vertical values are distributed in the red points. We have more of them over here and then fewer of them over here. We want to do the same thing for the blue points, and we want to do the same thing for vertical and horizontal. One way of capturing a continuous probability distribution is to use a parametric distribution. For example, we assume that the distribution is approximately normal, we compute the mean, we compute the standard deviation, and that would be the approximation for the distribution. Another alternative is to use a non-parametric model. So the difference here is that in a parametric model, all you need are the parameters. So for example, for a normal distribution, if you know the mean here and the standard deviation, you can compute everything, because this defines exactly the values over all the curve. A non-parametric model is something like we saw, for example, last week. We have things like k-nearest neighbors or kernel density estimation and so on, which we have parameters too, but the parameters alone do not specify everything. We also need, for example, the data to look up the actual values. So with naive Bayes you can do either, and in the assignment you're going to compare the parametric version, which is the one that is provided by scikit-learn, with a non-parametric implementation that you're going to create yourselves using kernel density estimation. So let's look at this particular example using kernel density estimation, which is analogous to what you're going to do. So your problem in the assignment has 4 dimensions, has 4 features. We cannot plot this kind of plot in 4 dimensions. I'm going to use, to illustrate the approach, I'm going to use this artificial data set that only has 2 features to make it easier to understand. So kernel density estimation, we saw briefly last week, is one way of trying to estimate probability distributions. Here I'm joining together 3 different ways. Let's suppose we have these values, these x's here represent values along this axis. So we have more points on this part, few points here, and then fewer points spread out everywhere. So if we plot the histogram, this is one way of representing the probability distribution with a histogram, for example. We see that we have more points here, fewer points here, and so on. Another way of representing this distribution is if we assume this is normally distributed, we compute the mean, which is somewhere here, the standard deviation, and we draw a Gaussian curve to approximate this distribution. But if the distribution is not normal, does not have that shape, this cannot be, maybe a pretty bad approximation. With kernel density estimation, we are adding a small, in this case using a Gaussian kernel, we add a small Gaussian curve for each point, and then we look at the sum over here. So this is the sum of all the Gaussian curves that these points are contributing, and the sum goes higher here because we have a larger density of points, is lower here because there are fewer points in this region, and so on. So this is what we're going to use, you're going to use in your first assignment, kernel density estimation. Scikit-learn implements this, so you can use the kernel density estimator in scikit-learn for the assignment. So let's apply this to this example. Let's consider this feature here that I'm representing in the horizontal axis. And now we are going to compute the probability distribution of this feature for each of the classes. So considering the red points, which is the red class, we're going to have this curve here. So a lot of points have values in this range, and then fewer points over here, and then practically none over there. So this is the curve that represents the density of points here using kernel density estimation for the red points. This is the same curve for the blue points. So you see there are lots of blue points on this side, fewer here, and then almost none over on this side. So we get a curve like this. And this is basically what we need for the naive Bayes classifier. We have the probability distribution of the horizontal feature for the red class and for the blue class. And now we do the same thing for the vertical feature. So you see lots of red points here, we have a bump here, and then fewer in the middle, a bit more over there, so we have this curve here for the red class. The same for the blue class, fewer points here, more points in this range, and we have the probability distribution of the vertical value here for the red and blue classes. Now, since we are assuming that given the class, the probability, the joint probability since we are assuming that given the class, the different features become independent if we fix the class, then when we need to compute the joint probability of the 2 features, x1 and x2, so these 2 directions, for the red class, we simply need the product of the features. So we multiply each of the values here for the feature x1, multiply that by the values of the feature x2, and we can get the joint probability, the estimate of the joint probability distribution for each point here. But note that this is only possible because we assume that they are conditionally independent given the class. That is to say, when we specify that they belong to the red class, then the features become independent. We can do the same thing for the blue class. We can compute the joint probability of the features for the blue class by multiplying these probability distributions for each of the features. And now you can see that in some regions on the plane, the red probability is higher, and in other regions the blue probability is higher. So if we also take into account the prior probability of belonging to the class, which in this case is not necessary because we have the same number of points in red and blue, So when we compare these probabilities, we can see where we're going to classify. So the blue region corresponds to those combinations of features which are more probable in the blue class, and the red, the ones that are much more probable for the red class. Now, one thing that we need to adjust here is the kernel width for the kernel density estimation. So remember from last lecture, if we use a very narrow kernel, we get more peaks and values in our estimate of the distribution of the values, and so we get something that has is a lot more intricate, a lot more curved in the frontier. If we broaden the kernel, then we average out over a larger region and we simplify the frontier here. So basically, we can make our naive Bayes classifier adjust better or lesser to the details of the data that we have, and there is going to be an optimal value that we can compute. So basically, we can use cross-validation. This is a result of tenfold cross-validation using different values of the kernel width, the parameter here, and we can see that for about 1.8 approximately, we minimize the cross-validation error. So this is the training error in blue. Of course, if we use a very low value, we get this very intricate curve, and we don't make any mistakes on the training set because the training set gets perfectly classified, but we get a very large generalization error, and we make a lot of errors outside the training set. If we increase the width of the kernel a bit, then things we can hit here the sweet spot where we minimize the validation error. If we keep increasing, then it becomes too flat and cannot classify this properly. So this is how you are going to optimize the kernel width for your naive Bayes classifier using your data. Note that you cannot do these plots in the assignment because these plots are possible if we only have 2 features. If we have 4 features, you would need a 4-dimensional plot, so there's no way we can do that. But you can do this plot because this is just a measure of the training error and the cross-validation error, and then figure out what is the best value for the kernel width. So this would be the final result. We have the naive Bayes classifier trained. We classify each point by considering the probability or adding the logarithm of the probability of having this feature if it belongs to class red, and this feature value if it belongs to class red, and comparing that with the same thing for blue. So in these regions, the ones on the red class win. In these regions, the ones on the blue class win, and this is where we separate the two. So another example, just to illustrate how you can apply naive Bayes classifier also to categorical data. So we don't have numerical features, we have categories, and we're going to do naive Bayes classification too in this case. Note that you cannot use logistic regression with categories, for example, because you need numerical values. I'm just going to run quickly through this example and show you the actual code. And the idea here is not that you memorize the example or understand everything at first, but just to give you some guidelines if you want to follow this step by step, because you have the whole implementation here. If you want to follow this step by step as a tutorial for helping you understand naive Bayes. So in this case, I'm going to give you the complete code because this is different from the one in the assignment. The one in the assignment has these continuous values, so you need to use kernel density estimation. Here we have categorical values, so we simply count the frequencies. And basically what we have, I'm going to increase zoom a bit this, we have these data on mushrooms. So there are edible mushrooms and poisonous mushrooms, and we have things like the shape of the cap of the mushroom, the surface of the mushroom, the color, and so on. And we have these different categories. So the shape of the cap may be like a bell, conical, convex, flat, and so forth. So you see all the features are categorical, and they are the description of the shapes of the mushroom. We have 22 features for each mushroom, and we have 2 classes. The mushrooms can be edible or poisonous. And we want to train a naive Bayes classifier to distinguish between the 2 classes. So first we have the data set on the mushrooms, which is simply set of strings like this. Each line corresponds to one mushroom. The first column specifies whether it is poisonous or edible, so P and E, and the other columns are the 22 features. So each letter is a code corresponding to the shape of the cap, the surface of the cap, and so on. So I'm going to show you how to implement a naive-based classifier for this example. For the assignment, you're going to have continuous features, so you're going to use the kernel density estimation, estimator, and you're going to compare this also to the naive-based implementation in scikit-learn. So let's start with listing all the features. I'm going to give you the example of the code using minimal features from Python. So I'm not going to use classes or dictionaries and so on. The code could be a lot simpler if we use more sophisticated constructs in Python, but this is just a basic tutorial. It doesn't matter if you know a lot of Python or not. The idea is that you can follow this to help understand naive-based classifier. So first, let's list all the features that we have. For all the possible values for the features that we have. So for the first feature, it can be a B for bell, C for conical, X for convex, and so on. And these values, this is a file with the list of possible values, and these values are all after the equal sign. So we can use the split there to split the string on all the equal signs, and then get the first character after at the start of each fragment to get the corresponding character, the code for that value in the feature. So basically this is what we do here, with the additional trick that we're also adding a possible value that is a question mark. This is because when we look at the data, in some cases we have an unknown feature, so a question mark can appear here in the each part of our data set. So when a question mark appears, it means that it's a feature that has not been observed, but we can deal with that by simply creating an additional category. So unobserved is an additional value for the feature. This is something that is easy to use when you have categorical features, because then you just add another category. Unknown is a category. It's not possible to use if you have numerical features, because there is no number for unknown, and then you have additional problems there. But in this case, we just add an unknown category, so all the features can be bell, conical, and so on, and also unknown, and that will the classifier will take that into account. So this is the result. This is for the first feature, the possible values, for the second feature, third, and so forth. Now we're going to load the data, and we're going to shuffle everything. So basically, we're loading the data file, and then we're going to loop through all the lines. We're going to remove the commas separating these characters, because you see there are commas separating all the characters. We just need the characters, and we're going to create a matrix with our 22 features. So we have 22 columns. Each row on our matrix is one mushroom, and each column in this feature matrix will correspond to one feature. But these are integer values, and we're going to put the index of the feature in these strings. So for example, for the first feature, B has an index of 1, C has an index of 2, and so on. This makes it easy to put everything in a numerical matrix. And we're going to do the same thing for the classes. So we're going to also create, add the classes here. And we have basically one matrix with the features, which has 22 columns for the 22 features, and one vector with the classes, where we say either poisonous or edible. So we put the index there for poisonous or edible. And now we're going to shuffle everything. But since we have these into two different matrices, we cannot simply shuffle one and then shuffle the other, because that will scramble the relation between each mushroom, the features of the mushroom, and the class. So what we can do is we shuffle a set of indexes. We create a set of indexes here, 0, 1, and so on. We shuffle that one, and then we return the feature matrix in that order and the classes in the same order. So both are shuffled, but they are shuffled exactly the same way. This is an important thing to do, or thing to take care about, because if you simply shuffle the features and then shuffle the classes, then you lose the correspondence between the features and the classes, and your classifier will not work. Okay, so take care with this kind of operations. Okay, so now we're going to build a sort of histogram, or basically counting the frequencies of each occurrence. For example, we're going to count how many mushrooms, or what fraction of mushrooms have a belt-shaped cap, have a conical shaped cap, and so forth. And this, we need this for the poisonous mushrooms and the edible mushrooms in order to use our naive Bayes classifier. Now, one problem that we can find is if in our data set we are missing some particular value. So suppose that by sheer bad luck, in the data that we collected, there were no mushrooms with conical cap. In that case, the count for conical cap mushrooms in some particular class would be 0, and the logarithm would be minus infinity, and so the classifier would consider it impossible to have a conical mushroom in that class. But this is not realistic. It may be just because by chance we didn't find any of those. So we can do some smoothing, this additive smoothing, which is to consider to always add a small value to the count. For example, we're going to add 1. That is to say, even if we don't find any example with that particular value on that feature, we always count as 1 having been found. We need to scale this, so when we compute the fractions, we are going to count the number of times each value occurs on that feature. We're going to add 1, but then we need to divide that by the number of examples, and added this value here, this alpha, multiplied by the number of different possible values we have for that feature. Because we're going to add this alpha for each different possible value, and so we cannot go over 100%. We need to keep this scale. So basically, the idea here is that we add a tiny amount so that even if it's 0, we still count as a very small probability, but some probability of finding that value. And this is basically what we're doing here. We're going to go through all the data, all the features and counting, but we start our count with at least 1. And then we are going to compute for our histograms the logarithm of the count that we did here, divided by this the total number of points plus the number of possible values for that feature, multiplied by alpha. But since alpha is 1, we don't need to multiply it. We just add the 1 there and add the total number of values in the feature. So this way we can have in this matrix, we have, or in this list, we have the logarithm of the fractions of each value for each feature. So basically the estimate of this. For each class, we know what the fraction was of mushrooms with conical cap, mushrooms with flat cap, and so on. And now we're going to split the data. So we have a fraction. We're going to leave a fraction for testing. And in this case, we're going to split into the edible mushrooms for test and for training, and the poisonous mushrooms for test and for training. So we'll have four sets here. The edible training set, the poisonous training set, the edible test set, and the poisonous test set. This makes it easy not only to train, because remember, in naive Bayes classifier, we need to consider each class separately when training, because we need to consider the probabilities of the features being distributed in some way in one class, in the other, and so on. So we're going to do that for the edible mushrooms separate from the poisonous mushroom. And then when we test, it's also useful to figure out what kind of mistakes our classifier is doing. So this is basically the core of the naive Bayes classifier. Once we have all these probability estimates, so the probability or the logarithm of the probability of having some value in each feature for each class, we can now classify each example by starting out with the prior probability of belonging to each class, and this can be computed simply by the fraction of examples in each class. So for example, if 70% of our mushrooms are poisonous and 30% are edible, we know that a priori the odds are 70% that a mushroom will be poisonous and 30% that will be edible. So this is the prior probability that we start with. And now we're going to add to the logarithm of the prior probability, we're going to add the conditional probability of each feature having that particular value for each class. So we're going to look at the histogram or the probability distributions for the edible mushrooms, and we're going to see what is the probability of having that particular value of that feature in this class. And the same thing for the poisonous mushrooms. And we're going to add these two, adding for the edible, adding for the poisonous, and now we check which one is larger at the end. If we end up with a larger sum for the poisonous mushrooms, so if poisonous is a larger total, then we classify this mushroom as poisonous. Since we started with the classes at 0, if this condition is not met, that is, if edible is larger, then we retain the classification of 0, which is an edible mushroom. So basically, this is the implementation for naive Bayes. We add up these logarithms of the probabilities for all the classes, and we pick the one that has the largest value here. So now we can put everything together, we get the features, we obtain the data, and we split into training and testing. We compute those probability distributions, those histograms, with the training data for the edible and for the poisonous mushrooms. We compute the prior probability, so this is just, we count how many edible mushrooms we have in our training data, and we divide by the total number of mushrooms, and the same thing for the poisonous mushrooms. And this gives us the prior probability of a mushroom being edible or poisonous. And now we're going to classify all the mushrooms, and we're going to compute the errors for the test set, for the edible and for the poisonous mushrooms. So this is an example of the results. For the test set, we are making mistakes 4.7% of the time, a total of 191 mushrooms that were misclassified, and we can see here the confusion matrix. So in this case, we are hitting most of them. So if the mushroom is edible, our model is predicting the mushroom to be edible most of the time. Some edible mushrooms, our model is predicting that they are poisonous. So this is bad because we are not going to eat those mushrooms, and maybe we could. But even worse is this case. So there are 178 poisonous mushrooms that our model is telling us they are edible. So this is actually a more costly mistake if we eat those mushrooms. So this is just an illustration of something we will see in more detail later on, but sometimes just minimizing the error may not be the ideal objective, because some mistakes may be worse than others. So if we don't eat a mushroom out of caution and we could have eaten, that may not be so bad as eating a poisonous mushroom and then dying. So this would be the worst case for mistakes, and don't use this classifier for eating mushrooms. This is just an academical exercise. So another different thing between naive Bayes classifier and logistic regression is that in logistic regression we were directly computing the conditional probability of belonging to a class given the features. This was our target function. We were computing the regression to that conditional probability of belonging to that class given that we know the features. And this is directly what we need to discriminate between examples. So if you give the features to the logistic regression classifier, the logistic regression classifier will give you the probability of belonging to each class, and that's what you need to classify the examples. However, the naive Bayes classifier computes the joint probability distribution. So what we are doing here when we use this expression that we have here is we are computing the joint probability distribution of each class and all the features. This means that we can then sample from that joint probability distribution and generate new examples, because we know what is the probability of having some particular features if we know the class. We can go back and forth in this case. So naive Bayes classifier is a generative classifier. Unlike logistic regression, you can use the naive Bayes classifier to generate new data. For example, we trained our naive Bayes classifier using this data. So this was the example I gave a while ago. And now we have the probability distributions of the x1 and x2 features for each class. And we can sample from those distributions to generate points from the red class and points from the blue class. So this would be an example of generating points at random using those learned probability distributions. Okay, so another thing that you're going to need to do for your assignment is to compare the classifiers at the end. So suppose that we train these three classifiers: logistic regression, K-nearest neighbor, and naive Bayes. We train them all in this data set. In this case, for logistic regression, we did some expansion to the data too, so that it could draw this line curved like this. Otherwise, logistic regression is just a linear classifier. But we have these three classifiers, and we tested them in the same test set. And in the test set with 45 points, the logistic regression classifier makes 10 mistakes. The K-nearest neighbors does 6 mistakes, and naive Bayes does 1 mistake only. Now the question is, can we tell that one of these is better than the other? Is this difference significant, or can we attribute this difference just to random effects, just by chance in this data set? So to answer this question, we need to have some statistical test of our results. One approximate test to do this is to consider that as we reach an infinite number of trials, this distribution of the actual errors that we find when we test our classifier and the average error that it will make, or the true error of the classifier, will tend towards a normal distribution. So this would be the expression here. We have a normal distribution of the difference between the actual measured number of errors and the expected number of errors, which is the probability of making a mistake multiplied by the size of the test set. And the difference between these two divided by this expression here, so the probability multiplied by the size of the test set multiplied by 1 minus the probability, and computing the square root. So this is basically the approximation of the binomial distribution to the normal distribution. But if we have this expression, we can assume that this will have a normal distribution, so we can find the intervals for a 95% confidence level of having a certain number of errors at some distance from the true error or the true expected errors in our classifier. So this is basically the expression here. We can compute this delta value, the standard deviation, by this formula. N is the size of the test set, X is the number of errors that we made, and this gives us an estimate of the standard deviation. So the proportion of errors that we are making multiplied by n, multiplied by 1 minus that proportion, and then the square root of this. And with this approximation to the normal, we know that the true error of our classifier, so what on average the number of errors would be for a test set of that size, must be somewhere inside this range. The number of errors that we found minus 1.96 times this delta here, and the number of errors that we found plus 196 times this value. So if we apply this to our three classifiers, we see that for logistic regression, the actual true error with 95% confidence should be somewhere between 10 and 15. For K-nearest neighbors, between 3 and 9. Between 5 and 15, between 3 and 9, because this is plus and minus that value, and this one between 0 and 2, something like that. So this is an approximate estimate, and from this we can see that there is really no significant difference between these two, because there is an overlap of these intervals. So it's possible that they actually have the same true error, just happened by chance that they made different mistakes in this case. But for naive Bayes, in this case, it's very unlikely, because this one has a very low number of errors and a lower range, and falls outside the 95% confidence interval for the other two. So actually for this one it doesn't, it's at the extreme, but at least when comparing naive Bayes with logistic regression, we can say that they are significantly different. A better test is one that does not look simply at the number of errors, because this one can tell you if one classifier is better than the other, but this one can tell you if the classifiers are making statistically different mistakes. So it may be that they make the same number of mistakes, but they make different mistakes, and so they actually are not the same kind of classifier, or they don't behave the same. And this is McNemar's test for this kind of problems when we are comparing two different types of tests, to different types of diagnostics or something like that. So in this case, two different classifiers. What we do is we count the number of examples that one classifier got wrong but the other one got right, and vice versa. So this is the number of examples the first one got wrong and the second one got right, and this is the number of examples the first one got right and the second one got wrong. And so now we compute the difference between these two numbers. We subtract 1, square this, and then add these two numbers, and this expression here is distributed approximately with a chi-square distribution with 1 degree of freedom. So given this approximation, we can also look at the table and see what corresponds to a 95% confidence level. It's this 3.84. So if this fraction here is larger than 3.84, we can be 95% confident that the classifiers are different, because the probability of this happening by chance, if the classifiers behave in approximately the same way, is below 5%. So we can use this to compare pairs of classifier. If we compare logistic regression with k nearest neighbors, we get a 0.8, so it's far below this threshold. This means that they have no statistical differences. They are behaving statistically the same. The same if we compare k nearest neighbors with naive Bayes, but when we compare naive Bayes with logistic regression, we get a number larger than 3.84. So we can say with 95% confidence that these two classifiers are behaving differently. They are making different mistakes, different numbers of mistakes, so they are not doing the same thing. So our conclusion is naive Bayes. From here we can see that it is statistically different from logistic regression, and since naive Bayes has a smaller number of mistakes and it is statistically different from this one, we can say that it is better. In the other cases, we cannot say that with confidence, because it may just have happened by chance. So this is how we're going to compare the classifiers in the end. And now, just to finish, a small detail about the pre-processing of data. So far, regardless of whether we have classification or regression problems, we know that we are trying to predict some new examples, and we need to provide data, we need to provide features to do these predictions. And what we've been doing is to scale the parameters, so with normalization or standardization and so on, of our data set before we feed everything into the classifiers. But the question is, how should we do this? Should we do this on the training set or each training fold, and then apply the same rescale parameters to the test and validation sets? Or can we do this on the whole set once and not bother doing this again? So in theory, these are parameters that we are computing from the data. So we really should, at least theoretically, compute these parameters only on the training data, and then apply the parameters on the test or validation data. So if you are rescaling your data, if you are standardizing, for example, then those means and standard deviations that you compute, you should compute only on the training set and apply it to the test set. This is very natural to do when you have the sets already separated, as you have in the assignment, but when you have everything together, this may be a bit of a bother. But in theory, it would be the correct option, because otherwise you are using parameters computed on the whole set of data to adjust the whole set of data, including the test set. And this could lead to some bias on the results. However, in practice, statistics like the mean and all those values that we use for rescaling tend to converge very rapidly. So the results end up being almost the same. For example, suppose that we have 2000 points and they have this distribution. They are distributed along this value from 0 to 120, and they are mostly concentrated here and have this distribution. If you split at random 1000 to each side and compute the mean of 1000 of them and compare with the mean of the other 1000, you see that they tend to diverge only by 1% of the standard deviation of this distribution. So basically, if you take 1000 points at random and compute the mean for those, you get practically the same as any other 1000 points or the 2000. It would not make a difference. So if you have a data set like this, it's not worth the bother of computing the rescaling factors for the training set and then applying them to the test set, even though in theory that would be the correct approach. It will give you exactly the same values, so it makes no difference. However, it may be more complicated if you have some kind of segmentation of your data or some different things. So, for example, suppose that these values are the amount of money people spend on transportation when going to work or to school and so on. And we have different distributions for different cities. So some cities are more expensive than others. If our problem is to gather all the data from all the cities and try to predict for what people will pay in general in those cities, in any of the cities, without caring which city they come from, then we can just shuffle the data, and if the data set is large enough, we don't need to compute the mean and standard deviation for the training set alone, because it will give us about the same thing whether or not we compute for the whole data or just for the training set. So in this case, we can shuffle the data, we reorder everything. When we do cross-validation, it's better to stratify by city so that we have the same proportion of examples from different cities, so some from one city, some from another, and so on, and we keep the same distribution over all the folds, because we don't care about the city. We want to predict in general for any particular person in this whole data. So this would be the approach in this case. But now suppose that we have a different problem. We want to train our system, our predictor, for example, for a regression, with data from a set of cities, and we want to predict for new examples in other cities. This means that our model must be able, or our hypothesis at the end must be able to generalize from one city to other cities. In this case, since different cities have different distributions, we need to be careful to not shuffle all the cities together, because when we're doing, for example, cross-validation, we need to see what happens if we train with these cities and then try to predict the value for that city over there, and vice versa, because that is the problem we're trying to solve, training with a few cities and predicting outside those cities. And in this case, rescaling should be done with the training data with these cities before applying to the other one outside, because we have different distributions for the cities. And if you just rescale with everything together, then you are contaminating the results, because different cities have different distributions, and in this case it may make a difference. So the important message here, we're not going to go into much detail into this sort of thing. You have to think a bit about this in the assignment, and there is one question to answer, but we are not going to handle many practical problems with this kind of issues. But the main message I want to give you is that in machine learning, you should not try to memorize recipes. You don't try to memorize the steps that you need to do. You need really to understand why you're taking each step, because depending on the problems you're trying to solve, on the kind of data that you have, and these details, the steps may actually have to be different. So if you understand what you're doing, you can navigate safely those different kinds of problems. But if you just memorize the recipes, it's very likely that you're going to make a mistake and get the wrong results. Okay, so some brief words on the first assignment. You have a data set that has 4 features for each example. So these are features extracted from banknotes to distinguish fake notes from real notes. In fact, these are synthetic features I generated because the real data set is slightly different. But there's one thing that is a bit annoying in the real data set, is that they don't tell, for safety reasons, which are the true banknotes and which are the fake ones. So I generated a new data set inspired on that one, but it's the same. 4 features, and they are supposed to represent different features extracted from the scans of the banknotes. You're not going to do the expansion that we did with logistic regression for those examples, because you already have 4 features. We're going to use logistic regression as a linear classifier. You're just going to adjust the regularization factor, that C parameter there. You're going to compare 3 classifiers. The naive Bayes classifier with kernel density estimation, so similar to the red and blue example I gave earlier, that you're going to implement to solve this problem. You're going to compare that one with the Gaussian naive Bayes classifier that you have available in the scikit-learn library, and also with logistic regression that you have in the scikit-learn library. You're going to implement this naive Bayes classifier. For the kernel density estimation, you can use the object on scikit-learn. You don't need to implement the kernel density estimation itself, just use that one to get the estimate of the probability distributions. So you're going to optimize these parameters, the bandwidth for your kernel density estimation, which you're going to use just one value for everything, since it should be standardized first and so on. And you're going to optimize the C value for the logistic regression. And then you're going to compare the results on the test set using both the approximate normal and the McNemar's test. And you should submit your code, the plots that we ask, and a questionnaire that you have there, both in English and Portuguese. You choose one and you answer the questions in that form and submit the form. So check the page for instructions and regular updates, because if you have some questions, if many people have questions about some specific aspect, I may just add that to the instructions page. For this week and the next, the tutorial classes will be just for questions about the assignment. So it's to help out with any problems that you have, some difficulties that you may have with the code or understanding the assignment and so on. Okay, so this was a bit longer than usual. The next one will be a bit shorter to compensate, but what we covered here was this Bayes classifier. So the idea that if we have the joint probability distribution of features and classes, we can minimize the classification errors by picking the class that has the most probability, joint probability, with the features of each example. However, we cannot do this in general because the joint probability distribution is too hard to estimate. With the naive Bayes classifier, we take an assumption that simplifies things, which is that for each class, the features are statistically independent. And this means that we can just multiply the probabilities of having each particular value, and we simplify the expression a lot. Now, this is not true in practice in most examples. It's not true that in each particular class the features magically become independent. However, naive Bayes classifier works fairly well in practice because we are just looking at the class that has the largest probability. We don't particularly care if the probability itself is very well computed or not, because when we compare the different classes, we pick the one with the highest value, and that's generally the correct one in many applications. So actually, naive Bayes classifier, both for this property and for the ease with which we can deal with categorical data, numerical, continuous data, whatever kind of data that we have, it's very flexible in that sense. So it tends to be used for many applications. We saw the difference between parametric and non-parametric models. So remember, non-parametric models may have parameters too. For example, in kernel density estimation, you need to parameterize the width of the kernel, but they are called non-parametrics because they are not fully determined by the parameters. You also need the data to compute the actual distribution, for example. The difference between generative and discriminative classifiers is that a discriminative classifier, like logistic regression, only gives you the conditional probability of belonging to the class once you know the features. And this does not allow you to compute the features for each class or to generate new points. With generative classifiers, you are computing the joint probability distribution, so you can go either way. You can classify or you can generate points for the different classes. And then we saw these details about comparing classifiers and pre-processing the data. So I recommend that you take a look at these sections of the books. And we're going to take a short 10-minute break, and we'll continue at 20 minutes past 5 for the second lecture. Okay? See you soon.